Well, you've probably felt the last couple of weeks of lecture have been quite hard going as we've been building the general abstract tools to study semi-simple Lie algebras. I guess that's fair. But now we're kind of coming to this most important place in the whole development where we're starting to see some combinatorial data emerging out of a semi-simple Lie algebra. So if you've kind of felt that you've got a bit behind recently, now is the moment to kind of start really focusing hard on this next part of the development. This is kind of the most important place, and I think it's fairly concrete suddenly. So now we're in the setup that G is going to be a semi-simple Lie algebra. And I'm going to fix a choice of T a maximal toral subalgebra. And I'm going to just write round brackets just for some non-degenerate symmetric invariant bilinear form on G. Of course, I have in mind that it's the killing form. But it's handy to allow a little bit more freedom in choosing this form. You know, when I work with classical Lie algebras, I much prefer to work with the trace form tau, and that's just as good for our current purposes. So we've established the Cartan decomposition. We did this in the last lecture. We showed that G decomposes as T together with a direct sum over so-called roots alpha of root spaces. And we showed the hard work that we did. We showed that actually T is exactly equal to the zero weight space. That's the centralizer of T in G. And then this R here, that was the set of roots. So that was the set of non-zero elements alpha in T star, such that G alpha is non-zero. And the general notation G alpha meant the set of all x in G, such that hx is alpha of hx. This is for all h in T. So that's the so-called alpha weight space of G with respect to the adjoint action of T. So we did all that stuff, and I guess the other thing we did is we observed that the restriction of that bilinear form, I guess we have the killing form, but the argument just involved the associativity property, so it would work for any other non-degenerate invariant bilinear form on G, that restriction of that form down to T cross T is also non-degenerate. So those are all results that we've established now. I want to actually do an example before we go any further. Let's have in mind one concrete example. And the concrete example is when G is the Lie algebra SLN of C. So we've shown this is semi-simple. It's even simple, it's easy to see that right away. And I'm going to let T be the subalgebra of trace zero diagonal matrices. So all elements of T, they're diagonal, so they're certainly semi-simple in the natural representation. And so it follows that T is definitely a toral subalgebra. You can see right away, actually, it's kind of as big as it could be, right? It's all trace zero diagonal matrices. So it's pretty much immediate in this case that this is actually a maximal toral subalgebra. But I don't need that right now, and I'll explain why maximal follows in just a second. But let's have a little bit more notation. So this T has basis H1, H2 up to Hn minus 1, where I write Hi for the diagonal matrix with just 1 and a minus 1 in the ith and the I plus 1th entries. I'm also going to let epsilon I in T star be the function that takes a diagonal matrix to its ith diagonal entry. So these span the dual subject to just one linear relation. T is n minus 1 dimensional. There's n of these epsilon i's, so there's one too many of them to be a basis. They span subject to one linear relation, and that's just the epsilon 1 plus. They all sum. Well, the sum of the epsilons, that's the function which takes a diagonal matrix to its trace, and we're looking at trace 0 diagonal matrices, so that sum is just simply 0. That's the one linear relation between these epsilon i's. But that's my preferred coordinates for T star. Okay, and then this G, here's its Cartan decomposition. It decomposes as T together with the direct sum over all I not equal to J. So these are all the off-diagonal matrix units, just the C span of them. So if I have a diagonal matrix in T, I've made this calculation before, but I'm going to write it out again because it's so important. If you do the matrix product HEIJ, you just get TI, that's scalar, times EIJ. Or if you do EIJH, you multiply the matrix unit on the right by that diagonal matrix, you get the scalar TJ EIJ. So in those places here, I'm just doing matrix multiplication. And that implies that the bracket H with EIJ, it's TI minus TJ EIJ, but it's better to write that as epsilon I minus epsilon J of H EIJ. That's just the scalar TIJ written in a fancy way. So this calculation shows several things. Well, first of all, it shows that the 0 weight space of G is T. It shows that the set R, the root system, it's the set of all of these epsilon I minus epsilon J's for all I and J with I not equal to J. None of these are 0, right? So that accounts for everything except for T. So T has to be the entire 0 weight space. And because T is G0, T is self-centralizing, it immediately follows that actually T is maximal as a toral subalgebra of G. Okay, so now we've got a maximal toral subalgebra. We've worked out the root system R. Each G alpha for alpha in R is one-dimensional. I mean, the root space is spanned by EIJ for the root alpha epsilon I minus epsilon J. And you can even work out what the killing form is. Let me see. I'm not going to use... So let's say that our form is tau, the trace form. I really prefer the trace form rather than the killing form. It's much more nice normalization. Then if you look at these gram matrix. So this is the gram matrix of this form. So I'm going to look at the basis Eij and its transpose Eji. Remember, these G alphas kind of come in pairs. G alpha is paired with G minus alpha. So this is one of these alpha minus alpha pairs of basis vectors in our basis. Alpha is epsilon I minus epsilon j, that spans G alpha. And then Eji, that spans G minus alpha. And the trace form, it's just easy to see that this is the gram matrix for the trace form on that two-dimensional subspace of G. And then all of these different two-dimensional subspaces, as alpha varies, they're all orthogonal, and they're all orthogonal to H. And here's the gram matrix on H. H has its basis H1, H2 up to Hn minus 1. And the trace form's dead easy to compute here. It just looks like this matrix here. So that's the gram matrix of the restriction of the trace form down to T. And this matrix, by the way, it has determinant n. That's a little induction exercise, which is non-zero. So it is indeed non-degenerate. These guys are obviously non-degenerate on these two-dimensional subspaces. And then all of these different spaces that I've drawn the gram matrices on, they're all orthogonal with respect to our form. Okay, so we kind of have a pretty good handle of what this Cartan decomposition is looking like. Right here, this is the Cartan decomposition of G with respect to this choice of maximal toral subalgebra T. So that's a very concrete example. As I'm going through the general theory in just a second, it'll be helpful just to kind of keep referring back to this SLN example to see what everything is in this case. But now I want to go back to the general case. And I want to develop in general, for an abstract semi-simple Lie algebra, I want to develop properties of the root system. Okay, so I'm going back to this general notation. I've got G fixed, I've got T fixed, and I've picked some invariant non-degenerate form, perhaps the killing form, but I don't want to insist on that. So we've already observed that the restriction of this form down to T cross T is non-degenerate. That was just something I think I only proved it for the killing form last time, but it just followed from the associativity of the form. I'm going to use it to identify T with T star. So that's something that's kind of always done in this subject. You use your choice of non-degenerate bilinear form, usually the killing form, to identify the maximal toral subalgebra T with its linear dual. So an element lambda in T star is going to be identified with what I'll denote by T sub lambda in T. And so here's how the identification goes. The inner product of T lambda with H is going to be lambda of H for all H in T. So that's the canonical identification of T with T star coming from that non-degenerate bilinear form, which probably is the killing form. I need to observe that the root system R, which is a subset of T star, it actually spans T star. Let's prove that. Well, if it doesn't, you could find some non-zero element H in T, so alpha of H is 0 for all alpha in R. If that didn't span, you could find some alpha that vanished on the span, but didn't vanish on everything. But then the Lie bracket of alpha with G alpha, well, remember, things in T act on G alpha as alpha of H, so that's acting by the scalar alpha of H, but alpha of H is 0. So this is for all alpha in R. So actually this H lies in the center of the Lie algebra G, but being as G is a semi-simple Lie algebra, its center is 0, and that's a contradiction. We assumed our H was non-zero earlier. Great. So now I'm going to take a root alpha. The restriction of this form down to G alpha is 0, but the restriction of this form, I should write G alpha cross G alpha. Well, I'm just going to write it like that. That's good enough. The restriction of this form down to G alpha plus G minus alpha is non-degenerate. So this shows that minus alpha also belongs to R. And we can do the following. We can pick a non-zero element E alpha and G alpha. I know that feels like lots of choice. No matter what E alpha we pick, there's some F alpha in G minus alpha, so that the form E alpha F alpha is non-zero. That follows exactly from these two facts about the restriction of this form. No matter what E alpha we pick, we can find an F alpha so that E alpha F alpha is non-zero, and we can choose that F alpha so that it's actually in that kind of transposed, that opposite root space. So I know there's some choice here, which is going to be annoying, and we'll have to work on that choice. But I've made an initial choice for each alpha, some non-zero E alpha and G alpha, and then there's a unique, actually, F alpha in... Actually, no, we don't even know that's unique. There is at least some F alpha in G minus alpha, so that inner product is non-zero. So now let's work at kind of refining our choices just a little bit. So lemma 1. The bracket of E alpha and F alpha, well, it's going to be the inner product E alpha F alpha times T alpha. And we chose things so that that's non-zero, and of course T alpha is non-zero because alpha is non-zero. Okay, so that bracket E alpha F alpha is not 0. Second, the inner product T alpha with T alpha is non-zero. Hence, after rescaling F alpha, if necessary, we can assume that the inner product E alpha F alpha, which was merely non-zero before, but I'm rescaling F alpha, I can assume that that's equal to 2 over the inner product T alpha T alpha. So this lemma, it's all for alpha in R. 3, let H alpha be twice T alpha over T alpha T alpha. Then the bracket of E alpha with F alpha is actually equal to H alpha. You can see that right away because we've chosen things so that E alpha F alpha is 2 over T alpha alpha, and so that scalar times T alpha, that's exactly the definition of H alpha, right? So that's immediate, and H alpha E alpha is twice E alpha, and H alpha with F alpha is minus 2 F alpha. That implies after that little bit of rescaling, that these elements E alpha, H alpha, and F alpha, they span a subalgebra of G that's isomorphic to SL2 of C, because look, I'm getting these relations of our standard SL2 triple, EHF. Okay, so that's kind of crucial lemma, lemma 1. It's helpful to think about the example when G is SLN of C as above. And if you take your alpha to be epsilon I minus epsilon j, then you can take E alpha just to be the IJ matrix unit. In fact, that alpha root space was one-dimensional, so that E alpha, it's uniquely EIJ up to multiplication by a non-zero scalar. But let's choose the IJ matrix unit, and then this F alpha in the lemma, which is then uniquely determined because these root spaces are all one-dimensional, by the choice of E alpha, F alpha will just be the transpose matrix unit. And then it's easy to see this H alpha is just going to be a diagonal matrix, which is 0 in most places except in the ith entry where there's a 1 and the jth entry when there's a -1. Okay, so it's kind of very concrete. We're getting a nice bunch of elements. And those E, H, and F in this SLN case, they kind of obviously give a copy of SL2 sitting inside. All right, so we better prove this lemma. It's kind of, everything's kind of really quite straightforward at this point. Very nice arguments, well worth following every step here. So we know already that E alpha, F alpha, T alpha is non-zero. I'm going to take some H in T, and I'm going to look at the inner product H with E alpha, F alpha. By associativity of the form, it's H, E alpha, F alpha, which is, let me see, H acts on E alpha as alpha of H, E alpha, F alpha. And that's just, let me see, alpha of H is the same as T alpha H by the way I've identified T and T star. This is just scalar. But I can rewrite that as E alpha, F alpha, that's scalar, times T alpha H. This holds for all H in T, hence actually E alpha, F alpha equals E alpha, F alpha, T alpha. Right, because it's all H there, it's all H there. The bilinear form is non-degenerate. Of this form on T. That proves 1. Second part. So for the second part, all I have to do is prove that T alpha is non-zero. So let's suppose, for a contradiction, that T alpha is 0. But if that's the case, the bracket of T alpha with E alpha, remember T alpha acts on E alpha as alpha of T alpha. This is exactly alpha of T alpha. So this is just 0. And similarly, T alpha F alpha is 0. So the Lie algebra, so if I let G alpha be the span of E alpha, H alpha, don't have that, T alpha, and F alpha, it follows very easily that this is a solvable Lie subalgebra of G. In fact, its center is exactly spanned by this T alpha. This guy gives you exactly the center of this three-dimensional Lie algebra, and when you factor out the center, you get an abelian Lie algebra. So this is actually a nilpotent Lie algebra. But I'm going to use Lie's theorem now. It implies that you can find a basis for G with respect to which G alpha sits inside the upper triangular matrices. Okay, that's exactly Lee's theorem applied to this adjoint representation of this solvable Lie algebra. But then T alpha, which up to a non-zero scalar is the Lie bracket E alpha F alpha at this point. Right, by part 1. This is non-zero, so T alpha is basically the bracket E alpha F alpha up to a scalar. This, being a commutator, sits inside the derived subalgebra. But the derived subalgebra consists of nilpotent matrices in the adjoint representation. So whereas G alpha, I didn't know it could have zeros on the diagonal, when I take commutators, I'm supported strictly above the diagonal. This shows that add T alpha is a nilpotent matrix, but is also semi-simple because it's an element of our toral subalgebra. Right? All elements of T are semi-simple, so add T alpha semi-simple. But the only nilpotent semi-simple endomorphism is 0, so T alpha is 0, which is a contradiction. Okay, so that establishes part 2, and now we're virtually done. We'd better just finish off 3. I already explained how to prove that E alpha F alpha is H alpha. So remember now I'm defining H alpha to be twice T alpha over T alpha T alpha. So I'm kind of renormalizing, and that renormalization exactly gave that bracket. I've got to calculate H alpha E alpha. I'm after twice E alpha. But H alpha is 2 over T alpha T alpha T alpha E alpha. And that is just alpha of T alpha E alpha. Oh, but alpha of T alpha is T alpha by this identification. So this is 2 E alpha. And the proof that H alpha F alpha is minus 2 F alpha is similar. There we are, we've proved the lemma. Lemma 2. For a root alpha, the only multiples of alpha that belong to our root system are just plus alpha and minus alpha. We've seen that they both do belong, but there's no other scalar multiple of alpha that does. Moreover, the dimension of the alpha root space is 1. We saw that for SLN by our explicit computation. It's totally general. For any semi-simple Lie algebra, these root spaces are all one-dimensional. So actually the dimension of G, it's the dimension of our maximal toral subalgebra plus the number of roots, because all those root spaces are one-dimensional. Okay, so I'm kind of just going through proving these really fundamental lemmas for the structure of semi-simple Lie algebras. You see, we're getting kind of very strong properties falling out right away. So I'm going to let E alpha, H alpha, F alpha be as in lemma 1. So G alpha, the span, is isomorphic to SL2 of C. That's an SL2 triple. I'm going to let M be the direct sum over all complex numbers C of the root spaces for the of the weight spaces for the weight C alpha. Okay, I'm trying to show actually that the only ones of these that are non-zero, the only C alphas that are actually roots are plus or minus alpha. So now G alpha acts on M via the adjoint action, right? Because when you take, H alpha acts diagonally on each GC alpha. E alpha just adds alpha to your weight, right? It sends things in GC alpha to things in GC plus 1 alpha. And F alpha just subtracts 1. H alpha acts on GC alpha as the scalar. What scalar does it act at? It acts as alpha of C alpha of H alpha, but H alpha is 2 over T alpha alpha of T alpha, but alpha of T alpha is equal to, it's looking complicated down here, just 2C. But you see now, the totally decisive step is we're going to use what we know about the representation theory of SL2. We've got an SL2 triple, and we totally understand what the eigenvalues of H alpha can be on a finite dimensional representation of SL2, right? This right here, this M, it's a finite dimensional SL2 module. So the representation theory of SL2, it tells us that all the eigenvalues of H alpha are integers. It tells us that I'm going to have to write it on the next page. It tells us that GC alpha is 0 unless 2C is an integer, because those are the eigenvalues of H alpha in our SL2 triple. Okay, so all the C's that are relevant in the definition of M, the scalar multiples of alpha that belong to R, they're certainly half integers. Next observation is that G alpha, this SL2 that I'm looking at, it acts trivially on the kernel of alpha, right? So alpha is a map from T to C. So this guy here, this kernel, it's a codimension 1 subspace of T. That's just because if you have anything in this kernel, how does it act on E alpha? Well, it acts by evaluating alpha on that element of the kernel, but it's in the kernel, so alpha evaluates to 0 on all of those things. Similarly, how does something in the kernel act on F alpha? Well, it is by evaluating minus alpha on there, which is 0. So E alpha and F alpha act as 0 on the kernel, and of course H alpha commutes because we're inside this maximal toroidal subalgebra T. Okay, so G alpha acts trivially on there. So our M, it's got a great big 0 weight space. This kernel right there, there's the kernel. It's codimension 1, so that's dimension T minus 1. That's a whole load of trivial G alpha modules. And then we've got G alpha itself. That's a copy of the adjoint representation. So that was a picture of that kernel right there. That was dimension of t minus 1. That was in M. Loads of trivial modules. Then we've got G alpha itself sitting in there. Oh, but that contributes one more zero weight space. So we've already used up all of the zero weight space. And then there's going to be maybe some more stuff coming from the GC alphas for C's with 2C being odd. I'm just using representation theory of SL2. Remember, you get all these SL2 strings. If you have 2C, you have 2C minus 2, all the way down to 2 minus 2C minus 2C. So that would be an SL2 string. Since I've used up all the zero weight spaces already in stuff I see, there can be no zero weight space in the remaining SL2 strings. So I'm using our representation theory of SL2, so the only other GC alphas that appear that aren't already accounted for by G0, G alpha, or G minus alpha, they must be GC alphas where 2C is odd. So all of this shows that if alpha is in R, then minus alpha is in R, and G alpha and G minus alpha are one-dimensional because they're coming in there, and none of the other ones are contributing to this 2 or minus 2 eigenspace for the action of H alpha. Right? So this exactly shows that they're one-dimensional because that's all we're getting in there. Just one SL2 string to eat up one zero weight space. And moreover, it shows that if alpha is a root, then 2 alpha is not a root, because this is C equals 1 coming from alpha being a root, and we see that 2C, 2 times 1, it's not odd, so that it's just not there. It follows that we can't have any GC alpha being non-zero for 2C odd, right? So I'm saying that these guys actually don't appear because if one did, we'd have a one weight space, a one eigenspace for H alpha in the corresponding SL2 string. So we'd actually have that C equals a half, and we'd have a G a half alpha being non-zero. But our argument was for if alpha's a root, 2 alpha's not a root. If a half alpha was a root, then alpha would not be a root. I've explained that in a clumsy way. That's the end of the proof. Okay, so we've made a huge amount of progress. We really have a good handle on this Cartan decomposition. Now G is T, together with the direct sum of all the root spaces. In there we've picked these E alphas, which give a basis. These are all one-dimensional. And we've shown that there exists F alpha in G minus alpha, and H alpha being the commutator. So E alpha, H alpha, F alpha is an SL2 triple. And actually, the H alpha is twice T alpha over T alpha, T alpha. So we have a good formula for that guy. The H alphas, alpha in R, span T, because the alphas span T star, and the E alphas, alpha in R, span the rest. In fact, they give a basis for the rest. And we've shown that the dimension of G is the dimension of T together with the number of roots. This guy, by the way, it will be called the rank of G. And at the moment, it depends on our choice of maximal Toral subalgebra, but in fact, all maximal Toral subalgebras have the same dimension. This rank will be well defined. Okay, I've proved 2 lemmas. There's one more lemma, as we're slowly getting this structure of the root system to unfold. And so this final one is kind of the final decisive application of the representation theory of SL2. So now we're going to think about what happens if you have 2 roots that are not scalar multiples of each other, right? We've shown the only scalar multiples of a root alpha in R are plus or minus alpha. And now I'm going to look at a root that isn't plus or minus alpha. I'm going to let R and Q in the natural numbers be maximal, so that beta minus R alpha and beta plus Q alpha are roots. They might both be 0. Usually they'll both be 0. And the lemma says that all beta plus I alpha for I between minus R and Q, they all belong to R. So we have this complete string from this bottom one to the top one. Everything in between belongs to R. And beta of H alpha is R minus Q. Hence, beta of H alpha is an integer, and actually beta minus this funny number, beta of H alpha alpha, well, because that's R minus Q, that guy right there, it's easy to see that this is just one of these beta plus I alphas in here, so this actually belongs to R. And the proof of this is quite similar to lemma 2. We're going to let G alpha be as above, this SL2. I'm going to consider M, that now is the direct sum of all of these G beta plus I alphas. So G alpha acts on M via the adjoint representation again, because right, bracketing with the E alpha or F alpha, it just adds an alpha or subtracts an alpha. So yeah, M is stable. So this M, it's a finite dimensional representation of SL2. So we know that all of the eigenvalues of H alpha on M are integers. How does it act? H acts on G beta plus I alpha as beta plus I alpha of H alpha, which is what? That's beta of H alpha plus I, and then I need this alpha of H alpha, which is what? That's alpha of H alpha. That's the same as H alpha is twice T alpha over T alpha T alpha. We've done this before. Alpha of H alpha and that are equal. Okay, so it's beta of H alpha plus 2I. Now there's 2 cases. If beta of H alpha, which we know has to be an integer by representation theory of SL2, this is a finite dimensional representation. If this is even, then all are even. All of these numbers, because it's beta of H alpha plus twice an integer. And the zero weight space is one-dimensional. We're in this situation, beta's not plus or minus alpha, so none of these guys are 0. So all of these root spaces are one-dimensional by lemma 2. Maybe I should add that in there. So this is one-dimensional, or 0, by lemma 2. If beta of H alpha is even, then we've got some even eigenvalue of H alpha. So we're getting SL2 strings with just even eigenvalues, and any such has a 0 weight space in it. So we're getting a 0 weight space for sure, but the 0 weight space is one of these guys, so it has to be just one-dimensional. Or it could be that beta of H alpha is odd, then all of these numbers are odd, and then there must be a one weight space. But the one weight space must be one of these G's, so it must be one-dimensional. Either way, it implies that actually M is an irreducible G alpha module. And in the first case, all the weights are even, and the 0 weight space is one-dimensional, so there's just room for one irreducible G alpha module. In the second case, everything's odd. Again, there's just room for one SL2 string in here. Okay, so M is irreducible. Its highest H alpha weight is beta of H alpha plus 2q. Its lowest is beta of H alpha minus 2r. By the definitions of q and r, we have everything in between. By our SL2 representation theory, it's just one SL2 string. And moreover, the bottom one, the lowest weight, the lowest H alpha eigenvalue, must be minus the top one. So I think this means that twice beta of H alpha is 2r minus 2q, so beta of H alpha is r minus q, and that completes the proof of lemma 3. Okay, so these three lemmas are pretty decisive in pulling out the structure of this Cartan decomposition, the combinatorial nature of this root system, as we will see next time.